Tonight we fall into the heart of Messier 87, where a ring of fire frames a well of darkness, and light itself returns with secrets etched into its vibration. This is not just an image of a black hole. It is a map of invisible forces. Polarized waves sketch the coils of a magnetic helix. Faraday's fingerprints twist the angles, and a jet straight for thousands of light years betrays the power drawn from spin. From horizon to halo, order wrestles, chaos particles are made young again, and time moves in slow, deliberate breaths. Watch closely, the field is speaking and the universe is listening. Messier 87 stands inside the Virgo cluster, where hundreds of galaxies drift in a shared ocean of dark matter and thin hot gas, and yet the view keeps narrowing until it settles on a single gravitational engine at the galaxy's core. The host is an immense elliptical galaxy, a pale oval of blended starlight without the tidy arms of a spiral, the kind of system shaped by long history, by captures and collisions that heat and smooth its stars into a luminous fog. Around the galaxy, swarms of globular clusters move like ancient lanterns, and through the core a linear wound of brightness cuts outward for thousands of light years, a jet that holds its line against the gentle disorder of the halo. The jet announces that the central object is not only heavy but active, converting in falling matter into focused outflow with an efficiency that dwarfs the furnace of ordinary stars. At the centre, a supermassive black hole gathers the gravitational authority of billions of suns into a region smaller than the orbit of the outer planets, a compact horizon whose presence is read in the motion of stars, in the temperature of gas, and in the way space itself steers light. Astronomers place the galaxy at roughly 55 million light-years a distance that softens any single heartbeat of change, but preserves the grand gestures, and they place the black hole's mass near 6.5 billion times the mass of the Sun, a scale that bends thought as easily as it bends trajectories. In such a setting, the background becomes the foreground diffuse cluster. Gas provides the reservoir the galaxy's stellar graveyard supplies. Dust and plasma and gravity sorts this material toward the nucleus, where turbulence and rotation take over. Matter that tries to fall in cannot do so in a straight drop. It carries angular momentum, and that momentum builds a swollen hot flow that skims close to the horizon before surrendering. The flow is not a quiet lake, but a magnetized storm. Even a weak seed field, once wrapped by rotation and squeezed by inflow, can become strong enough to guide charged particles, and particles that feel a magnetic field do not move freely. They spiral. Spiraling charges radiate, and that glow is not merely bright, it carries a memory of the path. The electric field of the light prefers a direction set by the geometry of the particle orbits, and the magnetic field that shapes them. That preference is called polarization. Once learned, the concept turns the galaxy's central light into a map. Where the electric field lines on the sky point together, order exists in the underlying field. Where they scatter, turbulence or tangled structure dominates. Messier 87 becomes a testbed because the engine is both large and luminous. The jet is visible across the spectrum from radio through optical and into high-energy bands, and the base of the jet lies close enough to the horizon that a single instrument using the longest baselines on Earth can begin to resolve the shape of the emission. This closeness does not erase mystery. It improves the questions. If a magnetic field threads the inner flow and the horizon, then the field may play the leading role. It can break the infall, extract rotational energy from the disk, and if it aligns with a spinning black hole, draw energy from the spin itself. That last possibility, in which a rotating horizon transfers power to a magnetized funnel, gains credibility when observers see a jet that remains narrow and coherent for thousands of light years, straightness on that scale implies a guiding structure that resists the quick growth of kinks and curls, and a helical or toroidal field can provide that spine. The galaxy's context adds another layer. The Virgo cluster is not static. Galaxies slide past one another, and through the cluster potential stirring wakes in the hot medium, and those wakes can feed the central engine in stuttering episodes. A slow drizzle of gas may maintain a persistent low-level accretion state for centuries, while occasional richer deliveries light the inner flow and briefly fatten the jet. When the delivery changes, the light changes and polarization is poised to show it. As radiation leaves the inner region, it crosses plasma that can twist its plane of polarization by a process called Faraday rotation, and thick or disordered screens can wash out the polarization fraction altogether. If the twist varies systematically with observing frequency, the amount of twist reveals the density of electrons and the strength and direction of the line of sight magnetic field in the material between source and observer. Thus, the polarization does not only speak for the engine, it also records the environment. The result is a layered story written in the orientation and purity of the light's vibration. The outer jet carries its own clues where knots brighten and fade, and the preferred directions of polarization rotate along the flow. The inner light closer to the horizon carries still sharper clues where the vectors bend around a ring of emission and suggest a structure that is neither random nor simple. The power of this approach lies in scale. The galaxy offers linked laboratories. The kiloparsec jet measures the durability of collimation and the reach of the magnetic spiral. The parsec region exposes the launch geometry. The horizon scale region tests how gravity and magnetism share control at the brink. In every layer, the same principle holds. Charged particles move in magnetic fields and their radiation knows the way. The narrative begins wide and grows narrow from cluster to galaxy to core to ring, as if zooming through nested shells of influence, and at each step the question becomes more intimate. What is the shape of the unseen field that orders this energy? How does that shape change when the intake of matter waxes or wanes? Where does the jet take its first breath? And how strictly does the field force that breath into a directed exhale? Messier 87 sustains these questions because it is near enough, bright enough, and large enough to be both recognizable and strange. In this first frame, the galaxy is not a distant ornament, but a machine that turns gravity into light and linear motion, and polarization is the instrument panel. The lines traced across the image are more than decoration. They are the fingerprints of a structure that stands against chaos, the quiet signature of a field that threads plasma guides particles and carves a straight path into the darkness beyond the halo. Early attention to Messier 87 begins with glass and silver and careful eyes, and before radio dishes rise from deserts and plains, a narrow thread in visible light already points outward from the nucleus like a taut wire. In the second decade of the 20th century, that linear feature enters the record as a curiosity, a line that looks too straight and too self-possessed to be a mere arrangement of stars or dust. It hints that the central region does not only hold mass, but also exports energy. As the century advances, radio astronomy opens a new channel. Long wavelengths, once dismissed as noise, become maps of charged particles spiraling in magnetic fields. Astronomers learn to recognize synchrotron radiation, the glow produced when fast electrons orbit field lines, and they discover that this glow carries polarization, a preferred vibration direction that remembers the shape of the field that guided the electrons. The galaxy's odd line becomes an outflow, and the outflow becomes a jet. With each improvement in sensitivity and resolution, the jet grows sharper. On the ground, the very large array sketches a collimated structure that stays narrow across hundreds of light years. In space, the Hubble Space Telescope reveals a chain of bright knots and filaments that step outward from the nucleus, their colours shifting in a way that marks the hard work of acceleration and the quiet fade of cooling. X-ray observatories add their own layer by showing high-energy knots that ignite and fade on human timescales, which is surprising for a structure stretched across thousands of light years. Polarization measurements begin to reveal the hidden skeleton. In visible light, the electric field vectors line up along the edges of the flow, as if a magnetic sheath wraps the jet and holds it steady, while in radio light the vectors sometimes swing toward being perpendicular, as if the interior field wounds around the beam in a helix. The pattern hints at a central spine and a boundary layer, a magnetic arrangement that can both accelerate particles and resist the tendency of a fluid column to kink. Interferometry turns hints into tests. By linking distant antennas, astronomers assemble a mirror as wide as Earth and use timing to create resolution. Very long baseline. Interferometry isolates the inner parsec where the flow tightens and turns from turbulence into a directed breath. Components near the core appear to move with speeds that seem faster than light, a geometric illusion produced when patterns ride a relativistic wind almost directly toward the observer. The effect is not a violation, but a sign of proof that the jet leaves the galaxy at a small angle to the line of sight and with enormous bulk speed. The alignment of structures across bands strengthens the story. The optical jet overlays the radio jet. The X-ray knots often coincide with radio features. The polarization direction swings with position in ways that match a helical field or shocks that compress field lines. Where a knot brightens, the polarization fraction can rise as if order briefly overwhelms turbulence. Where the flux dims, the fraction can fall as if tangled regions wash out the signature. The jet does not only carry power, it carries memory of the field that launched it. Yet each gain in clarity opens a new question. The jet remains almost absurdly straight over thousands of light years. What shapes a flow so far from its engine that local disturbances, side winds, and random density patches fail to twist it? A static, simple field would not survive so long. A purely turbulent field would not collimate so well. The observations suggest layered structure, a faster spine surrounded by a slower sheath, an ordered helical component imposed on a more chaotic background, shocks and reconnection sites that light up like warning buoys on a dark river. The galaxy offers case studies inside the flow. One bright knot famous for sudden outbursts flares in radio visible, and X-ray bands sometimes together and sometimes separately. When the flare rises, the polarization angle can swing, and the fraction can peak and then both relax as the knot fades. These cycles invite stories of magnetic reconnection, where field lines snap and rejoin, releasing energy that throws particles to higher speeds. They also invite stories of shocks, where compressive waves align the field and harden the spectrum. No single mechanism yet dominates across all events, and that uncertainty keeps the door open to a mix of processes. The core region changes too. On parsec scales, the radio core brightens and dims over months, and the location where the jet seems to turn from opaque to transparent at a given frequency shifts, with the mass flow a sign that the inner plasma resculpts itself as the intake varies. Faraday rotation, the twist in polarization angle imposed by plasma along the line of sight, sometimes appears large and sometimes small, and that variability hints at a screen whose density and magnetic direction change with time, Each twist becomes a measurement of electrons and field between the engine and the observer. Across these developments, the role of polarization is to translate light into geometry. An unconstrained brightness map shows where energy lands on the detector. A polarization map sketches the field that shaped the energy before it emerged. Where the vectors lie parallel to the jet shocks may have compressed field lines along the flow. Where they lie perpendicular, a wrapped field may dominate. Where the fraction is high, order wins. Where it is low, turbulence speaks. The persistent order of the outer jet, the apparent superluminal patterns near the core, the swings in angle during flares, and the frequency-dependent twists imposed by the intervening plasma, all point back to one conclusion. The magnetic field is not a passenger. It is the frame and the steering. The history from early optical discovery to modern multi-wavelength campaigns thus reads as a narrowing funnel. The outer jet proves that collimation holds across impossible distance. The knots prove that acceleration happens again and again. The polarization proves that the flow remembers a global, perhaps helical field. The geometry and the variability together insist that attention move inward toward the place where the field is set. If the outer beam is this stable and this structured, then the base must be more so, and the only way to learn its shape is to resolve the threshold itself, where gravity rotation and magnetic pressure negotiate the launch. The story of early eyes on Messier 87 therefore ends as a beginning. Instruments have followed the line back toward its source, and the last step is the hardest step because it asks for sight on scales where light is bent and time dilates. The patterns laid down by decades of observation set the boundary conditions for that final view and sharpen the questions that the next instruments must answer. The horizon comes into sight when an Earth-sized eye is assembled from radio observatories spread across mountains, deserts, and ice, and the scattered dishes become one instrument through the discipline of timing and the patience of combination. The Event Horizon Telescope is not a single mirror but a coordinated network that uses the method called very long baseline interferometry to let far-flung antennas act as facets of a single planet-scale aperture. Each station receives the electric field of the incoming waves and stamps it with time kept by an atomic clock. Later, in careful laboratories, the streams are aligned and interlaced until fringes appear, and distances on the sky become measurable, as if drawn by a compass with a span as wide as Earth. The campaign that leads to the first horizon scale image takes place over several clear nights in the month of April in the year 2017, when weather logistics and the rotation of Earth cooperate. As Earth turns, every pair of stations traces an arc through the Fourier plane, and those arcs taken together sketch a pattern of spatial frequencies that encodes the brightness distribution of the source. The atmosphere scrambles phases, so the teams rely on closure quantities that cancel shared corruption, a mathematical way of letting triangles of stations attest to the reality of a feature even when each single path is compromised. Hard disks fill with data at rates that would choke ordinary networks. Airplanes carry the captured waves to central facilities where the correlation is done. The crude first looks sharpen in stages as calibration finds its footing. What emerges is both familiar and new. The image released in the year 2019 shows a ring of light wrapped around a central darkness, with one side brighter than the other, so that the circle leans into a crescent. The darkness is not a hole carved in a luminous screen, but a shadow formed by the bending and capture of light around a compact mass. The ring delineates emission from plasma that glows close to the photon orbit, where paths of light can circle the black hole before escaping to distant eyes. The apparent diameter of that ring, measured in a few tens of microarc seconds, matches the expectations for a mass near 6.5 billion, times the mass of the Sun at a distance of roughly 55 million light-years, a check not only on mass but on the broad shape of space-time as described by the tested language of gravity. The brightness pattern is the signature of motion and magnetism. Electrons moving near the speed of light spiral along magnetic field lines and radiate a glow called synchrotron emission. On the side of the ring where the plasma approaches the observer, that radiation is boosted in brightness and squeezed in time. On the far side it is diminished, so the ring becomes a crescent. The direction of the brighter arc aligns with the axis of the large-scale jet known for a century in visible light and radiolight, binding the horizon scale structure to the outflow that runs for thousands of light-years. The image is not a simple photograph in the common sense, but an inference built on sparse measurements and disciplined caution. The Fourier coverage has gaps, the atmosphere breathes, hardware is imperfect, algorithms must choose a balance between fidelity to the data and a reluctance to invent detail. To protect against wishful thinking, multiple imaging pipelines with different priors and different regularizations attack the same visibilities. They return the same essentials: a ring whose size is stable under reasonable changes in assumptions, a crescent whose bright side points in the same general direction, and a central darkness that is not a hole in data, but a firm absence where light is expected to be missing. Within those essentials, uncertainties remain. The exact thickness of the ring, the contrast between bright and dim sectors, and any small departures from circularity carry systematic error. The array's geometry leaves blind spots in the Fourier plane. Refractive ripples in intervening plasma add subtle distortions that must be modelled. Calibration always leaves a residue. Yet the signal stands against those doubts, because the features that should be most fragile are the ones that persist when stations are removed, when days are separated, and when assumptions vary. Messier 87 assists this courage because its enormous mass stretches time. Where the compact source at the centre of the Milky Way changes on minute timescales, the engine in Messier 87 evolves over days slow enough that a picture crafted across a night does not blur beyond usefulness. Even so, when the data are divided by day, small shifts in the distribution of brightness appear suggestive of orbiting patches, ripples in the flow, or the play of magnetic turbulence. The ring is not a frozen emblem. It is a pattern translated from a living plasma, where gravity sets the rules and fields enforce the choreography. The physics written into this scene has more than one layer. Synchrotron emission carries a preferred vibration direction tied to the local shape of the magnetic field, and so the light's polarization promises a further map that can reveal whether the field near the horizon is tangled by turbulence, arranged by shear, or wrapped by rotation into a helix. The first image arrives in total intensity and proves the scaffolding. Later work will colour those bones with the directions of polarization vectors and the purity of the polarized fraction, turning the ring into a compass rose for invisible lines of force. Simulations that solve the intertwined equations of gravity magnetized fluid dynamics, and radiation had long predicted crescents like this one. The measurements both validate and constrain those models. Flows with too little magnetic flux fail to produce the observed brightness and asymmetry. Flows with too much flux produce rings that are too thick or too bright in the wrong places. A range of accretion states survives the first comparison, but the fence posts tighten, and the notion that magnetic fields play a central organizing role moves from taste to requirement. The link to the large jet is not an afterthought. The side that brightens on the ring is the side that points along the known outflow. That alignment is a hint that the inner field not only shapes the glow, but also sets the initial conditions for the beam extracting energy from rotation and guiding the first steps of the collimated wind. The first horizon-scale image therefore does not end with a portrait. It begins with a blueprint. It invites denser arrays to fill the missing spatial frequencies, higher observing frequencies to press closer to the photon orbit, and longer campaigns to watch the ring turn and flicker. It invites the full power of polarized light to draw the underlying field with lines and angles instead of mere brightness. The horizon is now a laboratory bench on which gravity, motion and magnetism place their instruments, and the next experiments will ask how the field near the brink takes hold of plasma orders it and then pushes it outward into a jet that remains a straight wound through a halo of stars. Polarization becomes the quiet grammar of light, a rule set that shows how charged particles dance in magnetic fields, and how that dance imprints direction onto the waves that arrive at a telescope. In ordinary glow, the electric field oscillates without a preferred orientation and averages to a soft wash. In polarized glow, the oscillation favors one plane, or a steady sense of rotation, and that preference can survive the long journey through space if the medium does not scramble it. Synchrotron emission, born when fast electrons spiral along magnetic field lines, is naturally polarized. In an optically thin region where the glow can escape without much self-absorption, the fraction of linear polarization can approach a large share of the total, while in an optically thick region the fraction drops and the preferred direction can swing. These simple tendencies turn light into a tracer of structure, because the direction of linear polarization on the sky is tied to the projected geometry of the field that guides the electrons. When the electric vectors line up tangentially around a ring, they sketch a toroidal field pattern wrapped by rotation. When they aim radially, they hint at a poloidal component that threads outward. Real plasmas blend these ingredients, and the pattern we read is the net of ordered strands and turbulent tangles. Circular polarization adds another subtler voice. In a magnetized plasma, linear modes can convert into circular modes when low-energy electrons and gradients in density and field strength are present, so a small but persistent circular signal can betray the character of the medium even when linear vectors look clean. For Messier 87, this grammar has special force because the central glow rises from hot magnetized plasma at the rim of the event horizon and at the base of the jet. There gravity drives motion to near light speed, rotation shears field lines into spirals, and compression strengthens magnetic tension until it can steer the flow. The light from that region is not a mere lamp, it is a map. A total intensity image shows where the energy lands on the detector. A polarization image shows how the invisible scaffolding of the magnetic field arranges that energy into order. The ring observed by the Event Horizon Telescope gives the stage. Along the side where plasma approaches the observer, Doppler boosting brightens the arc. Along the far side, the arc dims. Over that brightness, the polarization vectors add a second structure that does not simply follow the glow, but follows the field. If the inner flow has wrapped the field by differential rotation, an azimuthal component will dominate near the ring, bending the vectors around the darkness. If substantial poloidal strands survive, they will tilt the vectors and reveal a coupling that can carry energy and angular momentum outward into the jet. In this way, the geometry near the horizon becomes testable by inspection of angles drawn on the sky. Between the source and the observer, the message can be edited. A magnetized plasma twists the plane of linear polarization, an effect called Faraday rotation. The amount of twist grows with the square of the observing wavelength and with the density of electrons and the component of the magnetic field along the line of sight. If the twist is uniform, the vectors rotate together and remain coherent. If the twist varies within the telescope beam or along the depth of the emitting region, the rotated pieces can partly cancel and reduce the observed fraction, a process called depolarization. Thus, a single polarization measurement at one frequency is a hint. A sweep across frequencies becomes a probe of both the engine and the medium that covers it. The rotation measure extracted from how the angle swings with wavelength weighs the line of sight field in the electron column and turns the intervening plasma from a nuisance into a diagnostic. Turning these ideas into trustworthy pictures takes care. Very long baseline. Interferometry collects not only total power, but also the cross-correlations between orthogonal feeds that encode the polarized signal. Each station introduces instrumental leakage that can mimic real polarization unless calibrated away. Observers watch bright calibrators switch feed orientations and solve for the small terms that convert imperfect hardware into clean measurements. They test closure quantities that survive atmospheric corruption and ensure that the recovered vectors are tied to the sky rather than to the whims of a single antenna. Only then does a map of polarization angles become a map of the field rather than a portrait of the instrument. When such a map appears around a horizon scale ring, the pattern carries immediate meaning. A dominance of azimuthal polarization suggests that rotation has wrapped the inner field and that magnetic pressure and tension help to shape the last orbits of the flow. If the vectors bend but do not close perfectly, or if sectors show radial preferences, then poloidal strands likely remain and thread the compact object. Those strands matter because they provide channels through which the system can trade angular momentum, break the inflow and launch an outflow. And the fraction of polarization then adds a second constraint because a high fraction points to ordered regions with few reversals, while a low fraction points to tangled fields or to mixtures of differently rotated patches along the line of sight. Polarization also turns time into a diagnostic. When the intake of gas into the engine waxes or wanes, the density and temperature of the flow change, and so does the population of electrons that twist the plane. A denser or cooler screen increases the amount of rotation with wavelength, swings the plane more strongly, and reduces the observed fraction at long wavelengths. Higher frequency views peer through with less disturbance. On horizon scales, modest rearrangements of loops and filaments can swing angles by tens of degrees over days and change the fraction in step with total brightness, revealing whether the field is being stretched by shear, compressed by a passing shock, or reconnected in a burst that accelerates particles. The same swing traced across frequencies disentangles source changes from screen changes and turns variability into a ruler of depth. That is why the step from a total intensity portrait to a polarization map is a change in kind rather than a flourish. Brightness alone can be reproduced by many combinations of field and particle distribution. Polarization cuts that space because it insists on a geometry and keeps insisting across frequency and time. If the vectors curve smoothly around the ring, the field must be strongly wrapped. If the vectors align with the projected jet axis just outside the ring, the field must carry a long component that helps to collimate the outflow. If the fraction rises during a flare order has increased, perhaps because a shock compressed the field or a reconnection event carved a cleaner region. Each outcome is different in signature, and each signature is visible as angles and lengths for the vectors drawn on the image. In Messier 87, the story that emerges is of a magnetic scaffold that holds close to the event horizon and hands its order into the opening meters of the outflow. The same field that organizes the ring may also throttle the intake when flux piles up, creating a magnetically arrested phase that briefly pushes back on the inflow and reshapes the pattern until fresh matter relaxes the tension. The jet that runs for thousands of light years then inherits a helical imprint from those inner turns which helps it resist kinks and wander less as it threads the galaxy. In this light, polarized waves from Messier 87 are not ornaments, but messages in a disciplined script. They say that fields near the brink are strong, that order survives the heat and shear of plasma, and that the path from swallowing matter to launching a jet is written as much by geometry as by gravity. They also keep mystery alive because every twist recorded along the way may belong partly to the engine and partly to the screen, and only persistence across wavelengths, across nights, and across arrays will separate the signatures cleanly. The grammar is plain, but the sentences are long, and the meaning unfolds with each new campaign that reads the ring with sharper eyes, turning raw radio waves into a map of polarization around a horizon. Scale ring begins long before any image appears inside the careful rituals that preserve phase amplitude and orientation across a network spread over the planet. Each station of the very long baseline interferometry array records the electric field in two orthogonal feeds, often labeled to track distinct orientations, and stamps every sample with time from a hydrogen maser, so that remote streams can later be aligned within a tiny fraction of a wavelength. The weather above each dish adds its own wandering delay, the cables and receivers impose frequency-dependent ripples, and the feeds leak a little of one polarization into the other. The task is to reverse these insults without erasing the true signal from the sky. Correlation is the first act where recorded streams are brought together and shifted, until fringes appear, the characteristic oscillation that marks a shared feature on the sky. Closure quantities provide anchors in this sea of corruptions. A triangle of stations yields a closure phase that cancels station-based errors, and a quadrilateral yields a closure amplitude that is immune to independent gain mistakes. These robust combinations protect the signal that describes the source geometry, and they remain trustworthy when the atmosphere above one site hiccups, or when a receiver at another site drifts. Polarization rides on more delicate terms. The cross-correlations between the orthogonal feeds and those terms require a second layer of care. Instrumental leakage arises because no feed is perfect. A small fraction of the electric field meant for one channel bleeds into the other, creating a false polarized signal even for an unpolarized calibrator. Engineers and observers measure these leakage terms by watching bright sources through a range of angles, as Earth turns, letting the true sky polarization rotate, with respect to the feed while the instrumental pattern stays fixed. A simultaneous solution then separates the constant leakage from the rotating celestial vector. Feed orientation also matters. Some antennas rotate the feed to keep its axes fixed on the sky. Others allow the sky to turn with respect to the hardware. Unless these rotations are tracked and corrected, the recovered polarization angles would reflect engineering choices rather than astrophysical truth. The absolute angle on the sky is set by observing a source whose polarization angle is known from independent stable measurements, tying the interferometric map to a celestial compass so that a vector pointing east in the image truly points east in the sky. After these preparations, calibration proceeds in loops. Gains are solved from bright compact sources. Bandpass shapes are measured to flatten frequency response. Delays are fitted to align channels. Leakage is solved. Angles are set. And then the whole structure is refined by imaging and self-calibration that iteratively improves the model of the source and the estimate of the corruptions. The sparse coverage of the Fourier plane demands caution. The array does not sample every spatial frequency, so algorithms must choose how to fill the gaps without inventing sharp features that the data do not require. For total intensity, different imaging methods with different regularization philosophies are tried in parallel, and only features that persist across methods and across days are trusted. For polarization, the bar is higher. The crosshand data are weaker, The leakage solution adds uncertainty, and the risk of bias is larger. Teams therefore start with conservative priors prefer smoothness, unless the data insist on structure, and test the sensitivity of the recovered vectors to each piece of calibration. The result of this discipline is a vector map drawn on the ring, where each little line segment marks the direction of the electric field on the sky, and its length marks the fraction of light that is polarized. The angles contain the physics. Where vectors wrap tangentially, rotation has forged an azimuthal magnetic field in the inner flow. Where vectors tilt toward the projected axis of the jet, a poloidal component survives near the base of the outflow. The lengths also carry meaning. Long vectors signal ordered regions with few reversals inside the beam or along the line of sight. Short vectors signal tangled fields, mixed Faraday rotation, or gradients too fine for the array to resolve. To weigh the influence of intervening plasma observers repeat the measurement across frequency. Faraday rotation swings the angle by an amount that grows with the square of the wavelength, so a simple line fit to angle versus wavelength yields the rotation measure that encodes the electron density and the line of sight magnetic field between the engine and the eye. If the swing is small at the short wavelength used by the Event Horizon telescope, the screen is thin or hot near the source. If the swing is large at longer wavelengths seen by connected arrays on smaller baselines, the screen thickens outward into the parsec region. In this way, the same geometry traced at the ring dovetails with the broader environment traced just beyond it. Time adds a third dimension to the map. The ring is imaged on multiple days within a campaign, and each day's vectors are compared. Small but coherent changes hint at orbiting lumps in the emission zone, at waves that pass and compress the field, or at the shifting balance of poloidal and toroidal strands as flux is dragged inward. Across years, repeated campaigns watch the pattern again. If the preferred direction of vectors just outside the ring remains aligned with the jet axis, the coupling to the outflow is persistent. If the fraction rises during a brightening event order surges, if the fraction falls while the total intensity rises, turbulence or mixed rotation along the line of sight may have increased. None of these inferences hold unless the calibration is trustworthy, so every map is accompanied by null tests that scramble phases by imaging of calibrators that should show no structure, and by reconstructions using subsets of stations to ensure that a single dish did not imprint its peculiarities on the sky. The final product is not a photograph but a defended claim, a picture whose details survive changes in method in data selection and in prior. In the case of Messier 87, that claim is that the light at the brink is polarized at a substantial fraction, that the vectors curve around the dark center with a pattern consistent with a wrapped field, and that the amplitude and angle of the vectors imply a magnetic structure strong enough to matter dynamically. The map therefore graduates from ornament to instrument. It sets boundary conditions for simulations of hot magnetized accretion. It limits how much thermal plasma can sit between the source and the observer without over-twisting the angle. It connects smoothly to polarization seen on larger scales in the inner jet. Most of all, it gives the first direct glimpse of how gravity and magnetism divide authority at the edge of a supermassive black hole, with the field drawing a faint but legible sketch over the luminous ring that gravity has already revealed. The twisted vectors arrive as a second image layered over the first, a lattice of short lines draped across the crescent and around the darkness, and in their arrangement the hidden order of the field becomes visible. Around the brightest arc of the ring, the vectors tend to align approximately tangential to the curve, as if the magnetic field near the last stable paths of gas has been wound by rotation into an azimuthal band. Where the glow dims, the vectors still hold their course, bending along the rim rather than scattering, which argues against a field dominated by random tangles. Close to the minor gaps in brightness, the vectors do not evaporate. They shorten and lean, suggesting that pockets of mixed Faraday rotation, or changes in optical depth, shave the polarization fraction without erasing direction. The pattern survives across independent reconstructions and across days within the campaign, so the case grows that this is not an artifact of a single array geometry or a transient weather quirk, but the imprint of a persistent scaffold near the brink. That scaffold speaks to mechanics. In a rotating magnetized flow, differential shear drags initially modest field lines into loops around the spin axis, strengthening the toroidal component until magnetic tension can push back on the gas. The ring of polarized light with vectors that trace the rim is the footprint of that struggle. Where the vectors curl smoothly, the local field is coherent over scales larger than the resolving beam. Where the vectors show slight tilts toward the projected axis of the jet, a poloidal contribution remains threading outward and offering a conduit for removing angular momentum from the inflow. This blend of wound and open strands is the recipe for launching a jet that can both start narrow and stay narrow. The image therefore functions as a diagnostic panel. The curvature of vectors records shear. Their occasional tilt records linkage to the funnel. Their length records the balance between order and confusion. The fraction of polarized light around the ring is not maximized, which is as expected near a compact object, because temperature gradients, velocity gradients, and small-scale turbulence should all reduce coherence. Yet the fraction is far from negligible, and that alone contradicts models where the inner field is weak or mostly tangled. The bright side of the ring, boosted by motion toward the observer, also carries a slightly higher polarization fraction, which would be natural if compression by orbital shear or by weak shocks aligns the field more strongly where the plasma is moving fastest. Just beyond the ring in the sheath where the nascent outflow gathers, the vectors tend to rotate toward alignment, with the large-scale jet axis a handoff that links the horizon-scale geometry to the collimated beam seen on parsec and kiloparsec scales. The transition from tangential vectors on the rim to more axial vectors just outside the rim is subtle, but important. It implies that the toroidal dominance is strongest in the bright, gravitationally lensed ring, while a poloidal backbone asserts itself in the base of the outflow, a structure consistent with a helical field that changes pitch with radius. Faraday effects complicate and enrich this reading. Even at short millimeter wavelengths, a modest screen of thermal electrons near the source can twist the plane of polarization by a measurable angle. The fact that the ring vectors do not seem scrambled argues that the screen immediately surrounding the emission zone is either hot and thin or stratified, so that large rotation gradients do not coexist within the beam. On longer baselines at longer wavelengths, rotation measures large enough to swing vectors by many tens of degrees have been reported on parsec scales, which implies that the screen thickens outward. The combined picture is one of a relatively transparent core region wrapped by a denser, cooler sheath that imposes stronger rotation farther from the horizon. This stratification helps to explain why the inner vectors can be read so cleanly, while outer regions show more complicated behavior. Time variability adds another layer of meaning to the twisted map. Across the few days spanned by a single observing run, small shifts in vector orientation and length appear in concert with small shifts in the brightness distribution. Such changes could be produced by orbiting hotspots by patches of magnetic reconnection that briefly simplify local topology, or by waves that compress or rarefy the plasma along the rim. If a brightening sector of the ring simultaneously shows a rise in polarization fraction, the inference is that order is increased perhaps because a passing compression aligned field lines. If a brightening sector shows a drop in fraction, the inference skews toward mixed screens or newly stirred turbulence. Repeated campaigns across years then track whether preferred sectors of ordered vectors persist. In Messier 87, the broad sense of the pattern holds, suggesting that the inner field geometry is anchored by the overall flow rather than dictated entirely by short-lived eddies. The twisted vectors also challenge and refine models, simulations that inject too little magnetic flux into the inner region, struggle to reach the observed polarization fractions and fail to keep vectors coherent around the ring. Simulations that inject too much flux produce rings that are too thick or suppress variability that appears to be present. Models with a pronounced helical field predict a natural transition from toroidal dominance near the photon orbit to poloidal influence in the funnel, a behavior that the observed vector field appears to echo. At the same time, the precise balance between components is sensitive to the temperature of low-energy electrons that drive Faraday rotation, to the arrangement of density near the midplane, and to the distribution of non-thermal particles that actually radiate. The observed pattern therefore acts as a sieve, catching only those combinations of parameters that can both light the ring and draw the right lines across it. The scaffold view has large-scale consequences. A field that is strong and organized near the horizon can regulate how matter crosses the last orbits. If magnetic flux piles up faster than it can be swallowed, the inner flow can enter a magnetically arrested state, in which magnetic pressure pushes back on gravity and chokes the intake, modulating both luminosity and polarization as the system breathes. During such phases, the base of the jet can brighten, and its vectors can draw longer strokes as order increases. When the flux relaxes, the intake resumes and the vectors shorten as turbulence returns. On the scales of the kiloparsec jet, a helical imprint inherited from the base helps to suppress instabilities that would otherwise kink and disrupt the beam. Polarization maps at radio and optical wavelengths along the jet indeed show regions where vectors wrap the beam or align with its spine, alternating in a way that fits a helical field seen at changing pitch and viewing angle. Thus the ring vectors and the distant jet vectors are not separate stories. They are pages from the same logbook written in the same hand. The quiet triumph of the twisted vectors is to let a human eye watch magnetism at work near a place where space is curved and time runs slow. The lines do not simply decorate a famous image. They carry the weight of an argument that fields guide the final steps of infall extract spin energy and set the jet's initial twist. The remaining puzzles are not signs of failure but signs of closeness to the engine, where even a small change in density or field strength can swing a vector or dim a fraction. As more stations join, as higher frequencies press closer to the photon orbit, and as monitoring resolves slow turns of the ring, the lattice of vectors will either tighten around the current picture or reveal a more complex grammar. For now, the observed map already says enough to elevate magnetic structure from a background assumption to the leading actor that writes geometry into light. Faraday rotation leaves its fingerprints on the light that rises from the inner regions of Messier 87, turning the plane of linear polarization as the wave passes through magnetized plasma, and in doing so transforming a simple map of vectors into a layered probe of the medium between the engine and the eye. The rule is direct. The angle through which the plane rotates grows with the square of the wavelength, and with the column of electrons multiplied by the line of sight component of the magnetic field, so a single image at one frequency whispers, but a suite of images across frequencies begins to speak clearly. In an ideal uniform screen, the rotation is the same for every ray, so the vectors on the sky rotate together without losing their coherence, and one can march angle against wavelength squared to extract a rotation measure that weighs the hidden electrons and the magnetic direction of the intervening field. Real sources rarely offer such simplicity. The plasma near a supermassive black hole is not a uniform pane but a stack of changing sheets and filaments, and the emission itself may be mingled with the rotating medium. When the twist varies within the beam of the array, or along the depth of the emitting region, different pieces of the signal arrive with different angles, and the averaging in the telescope reduces the observed fraction of polarized light. This loss is called depolarization, and it comes in flavors that carry their own diagnosis. If the emitting region is mixed with rotators so that radiation is twisted as it is born, and as it passes through, neighbors differential, Faraday rotation within the source eats away at the fraction more strongly at long wavelengths. If the emission is clean but a patchwork screen sits in front of it, gradients across the beam produce beam depolarization, also growing stronger toward longer wavelengths. If the receiver integrates over a wide bandwidth, rapid angle swings across the band blur the vectors into a smaller net, a form called bandwidth depolarization that observers counter by dividing the band into many channels. The presence or absence of these signatures across frequency helps to place the location of the twisting plasma, and in M87 the pattern points to a stratified environment. On the shortest millimeter, wavelengths used to resolve the ring, the polarization vectors remain orderly, and the inferred rotation over the small span of wavelengths is modest, implying that the screen closest to the emission is either hot enough that low-energy electrons, which are efficient rotators, are rare, or thin enough that the column of electrons is not large. This fits a picture in which the inner flow is dominated by electrons with energies high enough to reduce their ability to rotate the plane, a relativistic effect that weakens Faraday rotation even in the presence of strong fields. Step outward to longer wavelengths where connected arrays probe the parsec region, and the rotation measures rise sometimes by amounts that swing vectors by many tens or hundreds of degrees, a sign that cooler, denser plasma in the sheath of the jet or in the inner torus contributes a thicker screen. The transition between these regimes suggests that the zone immediately around the photon orbit is comparatively transparent in the Faraday sense, while the region from the base of the jet outward contributes increasing twist and increasing depolarization. Time variability tightens this inference. Over days within a single campaign, the rotation inferred at millimeter wavelengths changes only slightly, while over months to years the rotation measured at longer wavelengths meanders, even reversing sign, which would be natural if the line-of-sight magnetic field in the sheath flips direction, as loops and filaments drift across the path. Such reversals argue for a magnetic environment with nested structures rather than a single coherent slab. The sign of the rotation measure records whether the average field along the line of sight points toward or away from the observer, and so a dance in sign is a direct witness of changing field topology, not merely changing density. Circular polarization adds a subtler fingerprint through conversion. In a magnetized plasma with gradients in density and field strength, linear modes can transform into circular modes as the wave propagates. A small but steady circular component in the core would then imply that low-energy electrons and suitable gradients are present near the base of the jet or within the inner accretion flow, even if the linear vectors look clean. The frequency dependence of this component growing toward longer wavelengths, where propagation effects are stronger, would support a picture of conversion rather than direct emission. Such a signal, when paired with the linear rotation, breaks degeneracies in the modeling of the plasma. because conversion depends differently on electron temperature than pure rotation. The fingerprints matter because they constrain the hidden population of particles that do most of the work on the polarization without radiating much themselves. The electrons that dominate the Faraday effect are not the highest energy ones that paint the ring in synchrotron light, but the lower energy ones that hide in the thermal pool. A low rotation at short wavelengths implies either a small number of such electrons near the horizon, or a temperature so high that their ability to twist the plane is suppressed, both of which narrow the menu of viable accretion states. A strong rotation at longer wavelengths implies that these electrons gather in a thicker layer beyond the ring, which matches the idea of a denser, cooler sheath around a hotter interior. The amount of depolarization then limits how tangled the field can be within the beam, and the scale at which the fraction drops with wavelength identifies whether gradients sit inside the emission or outside it. All of these inferences flow from the simple act of measuring an angle many times and watching how it turns. The fingerprints also refine the link between horizon-scale geometry and jet launching. If the rotation near the ring is small, the polarization vectors there are close to their intrinsic directions, so their tangential sweep is a true image of a wrapped field rather than a mirage produced by a twisting screen. If just outside the ring, the vectors start to tilt toward the jet axis, while the rotation grows, the base of the outflow likely carries a larger poloidal component and a thicker screen as expected if the funnel is filled with plasma drawn along open field lines. The coherence of vectors across millimeter frequencies, together with the stronger, sometimes sign-changing rotation at centimeter frequencies, thus argues for a field that is ordered at the brink and for a surrounding sheath whose magnetic direction and density vary on timescales of months to years. Each new campaign can then ask whether bursts of activity correlate with swings in rotation measure, whether a rising jet base thickens the screen and deepens depolarization, or whether reconnection events that briefly simplify topology also pare down the twist and let the intrinsic vectors shine more purely. In this way, Faraday rotation, once a nuisance that threatened to smear delicate maps, becomes an ally that writes conditions into the light. The fingerprints it leaves on Messier 87 do not smudge the evidence from polarization. They frame it, turning a ring of vectors into a stratified time-sensitive probe of the plasma that feeds the black hole and the sheath that carries the first breath of the jet. Faraday's fingerprints mark the road from the horizon to the eye, a quiet twisting of the plane of polarization that turns a map of magnetic geometry into a layered record of every magnetized parcel the light crosses. In a plasma where free electrons move under the pull of a magnetic field, the two natural modes of a radio wave are not equal. One runs a little faster than the other, and the difference in speed accumulates as the wave walks through the medium. The result is a rotation of the linear polarization angle that grows with the square of the wavelength and with the product of electron density and the component of the magnetic field that points along the line of sight. That rotation is not noise, it is a measure. Observers fold the angle against wavelength and read out a rotation measure that weighs the path through the plasma. If the rotation is uniform across the beam and across the depth of the source, the map of vectors keeps its coherence and the fraction of polarized light stays strong. If the rotation varies across the beam or from front to back within the emitting region, different parts of the signal arrive with different twists and partially cancel a process called depolarization. The mixture of rotation and depolarization is a soft but powerful ruler of conditions near the engine and in the sheath that surrounds it. In Messier 87, the ring lives at short millimeter wavelengths where the square of the wavelength is small and where the plasma near the source is likely hot and thin. The The ring vectors therefore keep their shape around the darkness, a sign that the local screen does not impose a wild differential twist within the resolving beam. This cleanliness does not mean that rotation is absent. It means that the combination of electron density, temperature, and line of sight field within the immediate source region permits the message to pass with little scrambling at this wavelength. At longer wavelengths, the story changes. On scales of parsecs, polarization maps begin to show larger swings in angle with frequency and reduced fractions that suggest stronger rotation and stronger gradients. The outer sheath of plasma, cooler and denser than the inner flow, imposes a heavier twist that can vary across the beam, and the inner jet collects these changes like paint picked up from brushes of different colors. The gradual thickening of the screen from the horizon to the parsec region explains why the most delicate map appears at the shortest wavelength, and why the larger scale jet, though still ordered, shows more complex patterns of angle and fraction. A second path to depolarization arises within the source itself. If the same electrons both emit and rotate, then different depths within the glow produce different amounts of twist, and the sum can cancel, even when the foreground is clean. This internal Faraday rotation is most efficient when a reservoir of lower energy electrons threads the hot radiating plasma. The presence or absence of such a reservoir in Messier 87 matters for more than bookkeeping, because low energy electrons also enable the conversion of linear polarization into circular polarization. That conversion, a cousin to rotation, leaves a small circular signal that can be used as a cross-check on the makeup of the plasma and the balance of field components. A consistent picture in which modest internal rotation, small circular fractions and clean short wavelength vectors coexist, points to an inner flow where thermal electrons are hot and sparse, where the field is strong and structured, and where most of the rotation builds in a sheath outside the ring. The line of sight magnetic field is a special player in this game. Polarization vectors drawn on the sky carry information about the field projected onto the plane of the sky, but Faraday rotation responds only to the component along the sight line. The two together make a three-dimensional clue. If the vectors around the ring are tangential, while the rotation measure stays modest at the shortest wavelength, the structure likely has a strong toroidal component with only modest line of sight flux in the immediate region. If the rotation measure grows quickly with distance from the core, a sheath with a stronger axial component and higher density may lie just outside. The sense of the rotation measure can even record the sign of the line of sight field. Changes in that sign along the jet would betray field reversals, perhaps from a helical pattern whose pitch and viewing angle evolve. In practice, disentangling these layers requires more than two frequencies. Observers use grids of bands from millimeter through centimeter wavelengths, linking the horizon scale view from a planet-size array to the parsec scale view from connected arrays, and to the kiloparsec view from very sensitive dishes. The slope of angle versus the square of wavelength is fitted piecewise, because a single uniform screen will not describe a path that crosses different media. Bandwidth matters too. If the rotation rate within the band is fast, the angle can spin through many turns across the channels, and the average can wash out into a deceptively low fraction, a bias called bandwidth depolarization. Modern campaigns cut the spectrum into narrow slices, derotate each piece to a common reference, and sum them in a way that rescues the hidden coherence. The need for such care is not cosmetic. Without it, an ordered field can masquerade as a tangled one. Time runs through these fingerprints as it runs through the vectors on the ring. When the intake of matter rises, density in the inner flow, and in the sheath increases, the rotation measure rises, and the plane of polarization swings more steeply with wavelength. A drop in intake can have the opposite effect. If a magnetically arrested phase develops, magnetic pressure in the core can evacuate or heat the nearest plasma, reducing internal rotation, even as the total intensity and linear fraction change in step with the restructuring field. Coordinated monitoring across wavelengths can therefore tell whether a change in polarization angle at a fixed band is due to new order in the field or to a thickening of the rotating screen. The timing of swings, their dependence on wavelength, and their correlation with brightening events together turn Faraday effects into a chronicle of the engine's breathing. The deepest value of these fingerprints lies in what they exclude. If near-horizon vectors remain coherent and the required rotation measure is small at short wavelengths, then models that fill the inner flow with a large population of cool electrons are disfavored. If the parsec scale rotation measures are large and structured, then a sheath of denser plasma is required, and that sheath must be magnetized in a way that preserves the long memory of a helical pattern. If circular polarization remains small but persistent, then conversion operates but does not dominate, and the electron distribution near the core cannot be purely thermal. Each of these exclusions tightens the space of plausible flows. Together with the direct geometry written on the ring, they point to a scene in which magnetic flux gathers near the horizon, wraps into strong azimuthal strands, threads into a poloidal backbone at the base of the outflow, and passes its order into a jet that keeps its shape across thousands of light years. Faraday's fingerprints thus do more than blur a picture. They are the marginal notes left on the manuscript of the light notes that record temperature density and field along the edges of the page. In Messier 87, those notes appear legible at the shortest wavelengths and more densely written, as the scale grows an arrangement that suits the narrative. Clean messages from the brink edited by a sheath, carried by a beam, whose memory of the launch remains visible even after a long journey through the galaxy's weather. The jet and its foot point meet where gravity, rotation and magnetic structure braid into a single engine, and the polarized ring now serves as a blueprint for that meeting. The bright arc that leans into a crescent marks plasma, skimming the last stable paths around the compact object, but just beyond that rim the vectors begin to tilt toward the large-scale jet axis, a change that reads like a handoff from toroidal order inside the ring to poloidal backbone outside it. In that transition lives the launch. A jet that survives for thousands of light years must begin with clear rules. Gas alone cannot keep a narrow column straight against pressure imbalances and small asymmetries, but a field wound into a helix can. The inner turns of that helix form near the horizon, where rotation in the accretion flow wraps field lines until magnetic tension rivals the weight of the gas. The same winding that draws the ring's tangential vectors also builds a magnetic pressure gradient that can expel plasma along the axis. That expulsion is not a simple push. It is a process that trades angular momentum between field and matter, so that some plasma is allowed to escape while the rest drifts inward. The foot point is the surface of compromise where the wrapped field hands, control to the backbone field, and where acceleration begins in earnest. Close to the compact object, the motion is constrained by a boundary called the light cylinder, a cylindrical surface where co-rotation with the field would require motion at the speed of light. Inside that surface, field and plasma are locked enough to share rotation. Outside it, the field lines can sweep back and fling plasma outward magnetocentrically. At greater heights and radii, the flow passes an Alfvén surface, where the bulk speed overtakes the speed of magnetic disturbances, and beyond that point the jet behaves more like a self-steering beam than a tightly anchored wind. The gradient of magnetic pressure, the centrifugal push along curved field lines, and the conversion of magnetic energy into kinetic energy all act together. The observed polarization pattern supports this path. Tangential vectors on the ring show a strong toroidal component. The gradual swing toward axial alignment just beyond the ring implies a poloidal guide that threads the base, and the persistence of order argues that the helical pitch changes smoothly with radius, rather than flipping between chaotic states. The jet power inferred from the brightness, and from the work done on the external medium, implies that the engine taps a vast energy reservoir. The rotation of the disk certainly offers one such reservoir, but the rotation of the compact object itself offers another larger one. If magnetic flux threads the horizon, the twisting of spacetime around a spinning mass can induce an outward flow of energy along field lines. In that picture, the foot point is not only the inner edge of the disk, but also the magnetized surface where gravity's rotation is harvested. The alignment between the bright side of the ring and the known jet axis supports this view, as does the need for a rigid spine to carry power far beyond the parsec scale. Polarization adds further clues to how the launch couples to the environment. If the base of the jet is threaded by a strong poloidal field, the rotation measure just outside the ring should be larger than directly on the ring, because the line of sight field component increases as strands rise and lean toward the observer. Observations that show growing twist with radius are thus signs of a thickening sheath that wraps the emerging beam. At the same time, the fraction of polarized light often dips in the immediate surroundings of the ring, before rising farther out, a behavior consistent with shear layers that mix ordered and disordered cells as the outflow bites into the slower plasma around it. Those layers matter because they regulate stability. A jet that carries only a toroidal field is prone to kinks. A jet that carries a blend with a poloidal spine and a toroidal sheath resists them longer. Knots along the kiloparsec jet carry the memory of how steady this balance is. When a knot brightens and its polarization vectors align more strongly, it is as if a passing shock or reconnection event has tightened the local helix and accelerated particles. When a knot dims and the fraction falls, turbulence likely has softened the order. These signs begin at the foot point, and the fact that the ring vectors already show coherence argues that the launch condition is firm. The foot point is also where the budget of particles is set. The jet cannot remain bright for thousands of light years unless fresh acceleration occurs along the way, but the first population of relativistic electrons must be born near the base. Polarization helps locate the seed. A rise in fraction together with a hardening of the spectrum in the inner parsec region would favor shocks near the base. A rise in fraction with little spectral change would favor reconnection that tidies the field without bulk compression. Early signs in Messier 87 hint that both operate at different times a mixed economy that can reconcile the steady global shape with intermittent flares. The foot point also negotiates with the intake. When magnetic flux accumulates faster than it can be digested, the inner flow can enter a magnetically arrested state, in which magnetic pressure near the compact object becomes strong enough to slow accretion. During such intervals, the base of the jet can grow brighter and more ordered as the field stiffens, and the polarization vectors near the ring can lengthen and tilt more cleanly toward the axis. When the flux relaxes and the intake resumes, the base softens and the vectors shorten. The alternation of these phases over months to years could explain why the parsec region sometimes shows strong rotation measures and strong collimation, and at other times appears looser. The foot point in this view is not a fixed ring, but a breathing zone whose shape and power respond to the local balance of inflow and magnetic pressure. The large-scale environment completes the circuit. A jet that begins with a strong poloidal spine can burrow through the interstellar medium of the host galaxy with less sideways spread. The pressure of the surrounding hot halo guides the beam and recollimation shocks form, where internal and external pressures balance. Polarization maps far down the jet show alternating bands where vectors wrap and then align a pattern that echoes a helix whose pitch slowly changes as the jet exchanges energy and momentum with its cocoon. The fact that the jet in Messier 87 stays straight across thousands of light years says that the initial twist and spine depth set at the foot point are adequate to the long road, and the ring's vectors specify that twist. The immediate promise of the polarized ring is therefore predictive power. If the foot point truly blends toroidal and poloidal fields with a certain pitch, then higher frequency imaging that moves closer to the photon orbit should see the tangential pattern intensify, while the axial bias just outside the ring sharpens. If the engine draws significant energy from the rotation of the compact object, then the brightness asymmetry of the ring should maintain a stable orientation over many years, tied to the spin axis even as the detailed substructure flickers. If magnetically arrested phases are common, then episodes of high polarization fraction at the ring should coincide with stronger collimation and higher rotation measures in the parsec region months later, as the stiffer base impresses its order on the sheath. In this way, the foot point ceases to be an abstraction. It becomes a testable zone identified by a pattern of vectors and their changes where the field near the brink sets the jet on its way and tells it how tightly to coil. Messier 87, by placing this zone within reach of a planet-sized eye, shows how the quiet grammar of polarization can link a flicker on a horizon-scale ring to the straight line that cuts across a galaxy. The accretion flow around the compact object in Messier 87 sits at the center of a crowded debate because the polarized ring fixes certain features, while leaving room for multiple ways to arrange the plasma that feeds it. In one picture, the flow is hot thick and weakly magnetized, a turbulent stew where disordered fields braid and break, but never pile up enough to dominate the motion. In another picture, magnetic flux is so abundant that it gathers near the horizon until magnetic pressure rivals the pull of gravity, choking the inflow and forcing matter to thread narrow channels. The polarized map argues against the most disordered version of the first picture because the vectors around the ring are coherent, and the fraction of polarized light is not small. At the same time, the ring does not look over-bright or over-sharp, as would be expected if magnetic pressure simply froze the plasma into a rigid cage. The path between these poles is where the puzzles gather. The temperature of electrons is a first hinge. The glow we see comes from relativistic electrons that spiral in magnetic fields and radiate synchrotron light, but the electrons that twist the plane of polarization through Faraday rotation are often cooler and more numerous. If the inner flow held a large reservoir of such cool electrons, the rotation near the ring at the short millimeter wavelength used for imaging should be strong enough to scramble the pattern, yet the observed vectors are orderly. This points either to a high electron temperature near the horizon that weakens rotation, or to a scarcity of low-energy electrons there. A hot 2-temperature flow, in which ions carry most of the heat, and electrons ride along at a cooler, but still high temperature can meet that requirement, but then the total brightness must be explained without an oversupply of radiating electrons. Changes in the fraction of polarized light over days suggest that small adjustments in electron distribution or in the geometry of the field can alter the balance without collapsing the map, a sign that the flow is perched between order and turbulence, rather than trapped at either extreme. The strength and topology of the magnetic field are the second hinge. A flow that brings only modest flux to the horizon can still produce a crescent, but it struggles to keep polarization vectors coherent around the ring. A flow that brings too much flux produces artifact rings in many simulations that are thicker than observed, and leaves too little room for the modest but real variability seen across days. The ring's thickness and the persistence of structure from day to day suggest that magnetic flux is high enough to shape dynamics, but not so high that it locks the inner flow into a single rigid state. In other words, the system appears to live near a threshold where magnetic pressure sometimes pushes back on the intake, and sometimes yields a regime where phases of partial arrest and phases of freer inflow alternate. The location of the transition surfaces where different forces rule is another source of tension with models. The radius at which the flow becomes optically thin, the radius where magnetic disturbances cease to run ahead of the bulk flow, and the radius where co-rotation would require the speed of light together, define zones with distinct behavior. The polarized image seems to place the bright rim near the photon orbit as expected, but the degree to which field lines thread through that region and into the funnel is less clear. If poloidal strands are strong, there the rotation measure just outside the ring should be larger than on the ring, and the vectors should tilt more obviously toward the jet axis. Some reconstructions hint at this tilt, but not all agree on its strength, which can depend on the handling of instrumental leakage and the choice of regularization. The need to separate subtle real tilts from artifacts keeps this corner of the puzzle box opened. Composition adds a further uncertainty. If electron-positron pairs are abundant near the base of the jet, the inertia and the rotation signatures change in ways that mimic certain combinations of magnetic field and density. If heavy ions dominate, the inertia increases, and the same field produces slower responses in polarization. Observations alone do not yet decide between these extremes, but the modest rotation at short wavelength and the stronger rotation at longer wavelengths together hint at an inner flow that is pair-poor and a sheath that is richer in cold electrons. Inclination and tilt contribute to the complexity. If the inner accretion flow is slightly misaligned with the spin axis of the compact object frame dragging, can twist the inner region into a warped disk whose line of nodes precesses. Such a warp would imprint a slow drift in the orientation of bright sectors and a slow modulation in the vector field over months to years. The present data show small day-scale changes, but not a clear year-scale precession, which may mean that any tilt is small or that the relevant timescale is longer than the current baseline. This uncertainty leaves room for an elegant possibility, a flow that sometimes precesses slowly and whose polarization sways with it, but whose average over a campaign still looks like a stable crescent. Radiative efficiency complicates the ledger. If the flow is too efficient at turning gravitational energy into radiation near the horizon, the ring would be brighter than observed for the measured intake rate. If it is too inefficient, the observed luminosity would require an intake that should thicken the screen and increase rotation beyond what is measured. A middle ground where non-thermal particles are accelerated intermittently by reconnection or weak shocks and share the stage with a dominant hot thermal pool fits both the ring and the variability. In such a state, brief episodes of reconnection can increase order locally, raising the polarization fraction without an enormous change in total flux, while other episodes inject turbulence and reduce the fraction as brightness rises. The tension between models and observations therefore does not read as a contradiction, but as a narrowing corridor. The corridor is drawn by the polarized ring, by the small rotation at short wavelength, by the stronger structured rotation at longer wavelengths, by the day-scale flicker in vector direction and length, and by the century-scale straightness of the jet. Within that corridor, the most plausible picture is a hot magnetized flow that delivers substantial but not overwhelming magnetic flux to the horizon, that sometimes approaches a magnetically arrested state and then relaxes that accelerates non-thermal particles in short episodes, and that hands a helical imprint to a jet whose spine remains poloidal enough to resist kinks. The remaining puzzles point to specific tests. If phases of partial arrest truly occur, the polarization fraction near the ring should correlate with later increases in rotation measure on parsec scales, as the stiffened base imprints its order on the sheath. If electron-positron pairs are rare near the core, circular polarization produced by conversion should stay small and track gradients rather than bursts. If a slow warp exists, long campaigns should reveal a gentle drift in the orientation of the crescent and in the angle of the vectors just outside the ring. Each test binds a parameter that models currently leave free. Until those tests are met, the accretion flow in Messier 87 remains a precise but unsolved riddle, a plasma that must be hot but not wasteful, ordered but not frozen variable, but not chaotic, and threaded by a field that shapes both the ring it lights and the jet it launches. Time that flickers becomes a tool when light from Messier 87 is watched across bands and across seasons, because the inner engine does not hold perfectly still. It breathes. Some nights the crescent brightens on its forward side, and the polarization vectors grow longer and more orderly, as if shear has tightened the field. Other nights the same arc softens, the fraction of polarized light dips, and tiny tilts appear as if turbulence has entered. These changes occur over days on the horizon scale, which for such a massive object is already quick, and they leave imprints that ripple outward along the base of the jet over weeks and months. Multi-wavelength campaigns gather these ripples by arranging radio arrays, millimeter arrays, optical telescopes and high-energy observatories to look at once, or at least to look within windows, narrow enough that the engine's slow clock can be trusted. At the shortest radio wavelengths, the Event Horizon Telescope resolves the ring and draws polarization vectors on it. At slightly longer wavelengths, connected arrays see the inner parsec where the jet becomes optically thin, and polarization vectors begin to turn toward the large-scale axis. Invisible light space telescopes and large ground telescopes map bright knots that sit far down the jet but still respond to upstream changes. X-ray observatories reveal high-energy flares in some of those knots, and occasionally near the core. Gamma-ray monitors watch for the most violent bursts, less frequent but telling. By comparing the timing of brightenings and of swings in polarization angle and fraction, observers extract lags that behave like distances measured in time. When the ring brightens and shows a rise in polarization fraction, a signature that can mean local ordering of the field or compression by a passing wave, the inner parsec often brightens with a modest delay, and its rotation measure can grow a sign that the sheath has thickened or that the line of sight field has strengthened. Weeks or months later, a downstream knot can brighten, and its polarization vectors can snap into cleaner alignment, as if a shock or a reconnection episode has been triggered by a disturbance launched near the foot point. Sometimes the sequence is not so neat. A knot far from the core flares without a clear trigger in the ring. In those episodes, the base remains calm while the distant sight accelerates particles locally, perhaps where the jet encounters a pocket of denser medium or where internal pressure imbalances create a slow shocks train. These differences are not contradictions. They record a jet that is both centrally driven and locally alive. On horizon scales, patterns shift over days as orbiting hotspots or turbulence cells sweep around the ring. An orbiting patch at a few gravitational radii completes a circuit on timescales of days for a mass of billions of suns, so a moving bright sector that waxes and wanes from night to night is consistent with such motion. If the same sector shows a temporary increase in polarization fraction, the feature likely carries a more ordered field or passes through a compression that aligns field lines. If the fraction drops while brightness rises, newly mixed Faraday rotation or tangled strands may be at work. Tracking these signatures across multiple campaigns begins to reveal whether a preferred side of the ring participates more often in such events, which would suggest a quasi-stable pattern in the inner flow, or whether the activity wanders, which would point to a more symmetric turbulence. The slowest changes arise from the intake. When the supply of plasma near the horizon increases, the inner flow densifies, the screen thickens, and rotation measures at longer wavelengths strengthen. The base of the jet may brighten, and over months the collimation can appear tighter as the poloidal backbone stiffens. When the supply drops, or when magnetic flux chokes the intake in a magnetically arrested phase, the ring can grow more polarized, even if the total intensity does not soar, because the field simplifies under tension. Later, as the phase relaxes, the downstream rotation measure can slacken, and the polarization fraction in the inner parsec can fall as turbulence returns. These cycles are not tidally periodic. They are breath patterns rather than metronomes governed by stochastic delivery of gas from the galactic environment, and by the nonlinear interplay of gravity and magnetism near the brink. Period searches in the light curves and polarization curves sometimes reveal hints of gentle rhythms on year scales, but the evidence remains soft, consistent with precession of a minor warp, or with repeat passages of a favored spiral in the flow, yet not firm enough to count as a clock. High-energy windows add a distinct accent. When X-ray flux from a downstream knot rises, the polarization angle in visible light can swing, and the fraction often increases, a signature of shock compression aligning the field. If a gamma-ray flare accompanies such an event, the particle acceleration must be vigorous, and models that invoke magnetic reconnection rather than pure shocks gain appeal, because reconnection can rapidly produce very high-energy particles without requiring a strong bulk compression that would leave a heavier mark on long-wavelength brightness. Correlations between X-ray flares and changes in the ring's polarization are harder to catch, because the ring varies more slowly, and because light travel and dynamical lags muddle the sequence. But the rare coincidences suggest that powerful disturbances launched near the base concede both local ordering at the ring and downstream acceleration. The orientation of the crescent itself has remained broadly stable across years, tying the bright side to the jet axis, which implies that the dominant direction of motion and of field near the base is fixed by the spin. Within that frame, the details shift, and the shifting is the information. Multi-wavelength polarization behaves like a set of interlocking locks. The ring constrains the geometry and the temperature of the innermost plasma. The inner parsec constrains the thickness and topology of the sheath. The optical and X-ray knots constrain the efficiency and location of particle acceleration farther out. When a change in one lock coincides with an expected change in another at the correct delay, the implied chain of cause and effect gains strength. When the expected partner does not move, the jet asserts its independence and teaches that local physics can dominate. The great benefit of such campaigns is that they turn a static portrait into a motion study. They replace a single polarization map with a film that shows vectors lengthening and turning, fractions rising and falling, and angles drifting in concert or out of step across bands. In Messier 87, the film so far argues for a launch that is steady in direction, but variable in vigor, a field that stays ordered enough to leave a readable helical signature, yet allows intermittent reconnection and shock formation, and a sheath that thickens and thins on humanly accessible timescales. The next steps are clear. Denser coverage at the shortest wavelengths, will watch the ring from night to night with less missing time. Better coordination with arrays that monitor rotation measures will catch the growth and decay of the screen with less ambiguity. High-energy observatories will keep testing whether the strongest flares downstream announce themselves at the base. All of it feeds back to the central mystery: how the geometry of a magnetic field near an event horizon writes a story that can be read in light, not only in a single frame, but through the slow, deliberate turns of time. Particles and power meet in the glow that spans from long radio waves to hard gamma rays, and in Messier 87 the spectrum is a ledger that records where energy enters the electrons and how it leaves. Synchrotron emission writes the low to mid-frequency pages, curvature radiation, and inverse Compton scattering. Write the higher pages, and all of them are shaped by the magnetic field that the polarization maps reveal. Near the ring, electrons must reach relativistic speeds to radiate strongly at short millimeter wavelengths, and farther out along the jet they must be renewed again and again to keep the beam bright for thousands of light years. 3 families of engines compete and often cooperate to accelerate these particles, shocks that compress and order the field magnetic reconnection that breaks and rejoins field lines to convert magnetic energy directly into particle energy, and turbulence that stirs the plasma and supplies many small kicks that add up over time. Each engine leaves a trace that polarization and timing can read. In a shock gas, moving faster than the local wave speed piles up against a barrier and converts bulk kinetic energy into heat and non-thermal tails. Field lines compress and partly align with the shock plane, raising the fraction of polarized light and rotating the preferred direction in a way that depends on the shock obliquity and the viewing angle. The spectrum hardens as newly accelerated electrons fill high-energy bins, and then it softens as radiative cooling trims the top. Where observers find a rise in polarization fraction, together with a swing in angle and a brief hardening of the spectrum, a shock is a natural culprit. In reconnection, oppositely directed field lines collide and snap, and magnetic tension accelerates charged particles in narrow exhausts and contracting loops. The field can become more ordered after a burst as small islands merge into larger structures, so the polarization fraction can rise even without a strong compression signature in total intensity. Reconnection also accelerates very high-energy particles quickly, which can produce X-ray or even gamma-ray flashes with only a modest radio echo. Where observers find a rise in high-energy bands and a cleaner polarization pattern near the base, without a broad shock signature in the ring, brightness reconnection stands out. Turbulence operates more quietly. Random motions at many scales scatter electrons and can drive a second-order acceleration that slowly lifts energies. Turbulence reduces the polarization fraction by mixing field directions within the beam and across depth, and in a variable flow it can intermittently seed both shocks and reconnection by building gradients and current sheets, where the fraction dips while the spectrum brightens modestly, and the angle jitters. Turbulence likely has the upper hand. The distribution of particles then feeds back into the polarization through Faraday effects. Low-energy electrons, which do not shine much at the observed bands, twist the plane of polarization and convert linear modes into circular modes as light propagates. A small rotation near the ring implies that such electrons are scarce or very hot close to the horizon, while stronger rotation farther out implies that the sheath around the jet base is richer in them. This profile sets the stage for where shocks or reconnection can be most efficient. If the base is hot and pair poor reconnection, there can accelerate electrons without drowning the signal into polarization, letting the intrinsic vectors near the ring be seen. If the sheath is cooler and denser, Shocks formed by pressure, mismatches along the early jet can align the field and light up radio and optical knots, and the associated rotation can mask some of the intrinsic order unless frequencies are chosen carefully. Spectral energy distributions across bands trace these regimes. A synchrotron component that peaks at millimeter or submillimeter, wavelengths near the core and then rolls off, can pair with an inverse Compton component that rises at X-ray energies, if local seed photons are available, either from the synchrotron pool itself or from ambient fields, while farther out a second synchrotron component from fresh acceleration can dominate the optical band with higher polarization fractions when shocks clean the field. In Messier 87 episodes where optical polarization rises sharply in a distant knot, while X-rays flare suggest shock acceleration with ordered post-shock fields, while episodes where the base shows only modest total intensity change but subtle tightening of vectors hint at reconnection near the foot point. The energy budget implied by the jet's work on the surrounding medium requires a reservoir larger than the local thermal pool can provide, and points back to magnetic energy drawn from rotation. In that sense, the field is both the accelerator and the battery. When magnetic flux piles near the horizon, a magnetically arrested phase can occur that stores energy and then releases it in reconnection, bursts sending packets of ordered field and energized particles into the funnel. The first steps of those packets may be visible as brief increases in the ring's polarization fraction, and as tilts that align more clearly toward the axis followed weeks later by brightenings in the inner parsec with higher rotation measures as the sheath responds. Over months, some of that energy emerges as downstream shocks that raise polarization in optical knots. The longevity of the jet then depends on how often these packets arrive and how the balance between acceleration and cooling proceeds. Electrons that radiate at optical and X-ray energies cool quickly in strong fields, which demands local reacceleration if high-frequency brightness is to persist far from the core. Radio-emitting electrons cool more slowly and can carry a memory of past events, so radio polarization maps show a layered archive where old episodes of order persist beneath new ones. Reading that archive requires care to separate intra-beam mixing from true field changes. But when the vectors rotate smoothly along the flow, and the fraction waxes and wanes, in step with spectral hardening, the case for a helical backbone punctuated by shocks strengthens. The role of composition threads through these arguments. If pairs were abundant near the base, reconnection could populate both signs of charge efficiently, but the associated Faraday rotation would weaken, and the observed modest but non-zero rotation near the ring would be harder to reconcile. If heavy ions carry a significant share of inertia, shocks propagate differently, and the conversion of magnetic energy into particle energy can be less efficient unless reconnection dominates. Current evidence from polarization and rotation favors a base that is not rich in pairs with ions, contributing mass, and with electrons carrying the radiative signature. That choice reverberates through models of acceleration and collimation. The final test of these engines rests in patterns that combine timing spectra and polarization. If reconnection near the horizon is common, there should be clusters of days where the ring shows higher polarization fraction without a large increase in total flux, followed by selective increases in high-energy bands. If shocks dominate the inner parsec, there should be periods where rotation measure rises and polarization vectors there align more strongly with optical and radio brightening together. If turbulence drives second-order acceleration during quiet spells, the spectra should harden gently while polarization fractions fall and angles wobble. Messier 87 has already displayed each pattern at least once, which argues that the jet's economy is mixed and adaptive, with different agents taking the lead as the magnetic and density landscape shift. What remains constant is the role of the magnetic field as both scaffold and fuel line. The same field that orders the ring and guides the first meters of the outflow also stores the energy that becomes the speed of the electrons, and the polarized light across the spectrum is the receipt that lists each transfer. Jet stability over thousands of light years is a paradox that Messier 87 presents, with a straight face, a rigid line piercing the host galaxy's soft halo, and polarization along that line offers the grammar of an answer. A beam of hot plasma pushed at relativistic speed through a surrounding medium should kink, shear, and tangle, unless a guiding structure resists those instabilities. The most natural guide is a magnetic helix whose pitch adapts with radius and distance, blending a poloidal spine that points along the axis with the toroidal sheath that wraps around it. Polarization maps along the jet record this blend by showing vectors that sometimes align with the spine and sometimes wrap the beam, switching in bands that echo the changing pitch of a helix under varying pressure. Where the vectors align with the axis and the polarized fraction rises, order has grown and the spine asserts itself. Where the vectors curl and the fraction dips, turbulence or mixing has gained ground, or the beam has passed through a shear layer where the wrapped component dominates. This alternation anchors the case that a helical field persists far from the base. Stability requires more than a pattern. It requires a mechanism that prevents small bends from growing. The most dangerous menace is the kink mode, a global twist that can snake through a magnetized column and break its coherence. A pure toroidal field is vulnerable to this fate because it lacks a straight backbone. A pure poloidal field resists kinks better, but struggles to confine the flow. A helix can do both if the pitch is right. Near the base, where pressures are high and speeds rise, the toroidal component helps collimate the outflow, but a poloidal core must be present to tie the beam to a straight path. As the jet expands, the ratio of toroidal to poloidal field changes and recollimation shocks arise, where internal pressure meets the pressure of the environment. These shocks compress and partially order the field, raising the polarization fraction and turning the vectors as if the helix were momentarily tightened. Bright knots that appear at such recollimation sites in Messier 87 often show increased polarization and cleaner vector patterns, as though the jet took a deep breath, straightened its coat and continued. Shear along the beam's edge is the second threat. A fast spine sliding past a slower sheath or a quiescent medium can develop Kelvin-Helmholtz waves that corrugate the boundary transfer energy and seed turbulence. Limb brightening, where the edges of the jet appear brighter than the center in radio or optical images, often accompanies such shear and polarization at the limbs, can align with the flow as compression and field line stretching occur along the boundary. In Messier 87, limb brightening appears in places, yet the beam does not shred, suggesting that the sheath is magnetized and that a helical field with the right pitch turns shear from a destroyer into a sculptor. The sheath can absorb perturbations, dissipate them into heat, and hand the spine back a narrower, more ordered cross-section downstream. Rotation measure gradients transverse to the jet strengthen the case for a helix. When one edge of the beam shows a larger twist in polarization angle with wavelength than the other, and when the sign of the gradient is consistent along stretches of the beam, the natural interpretation is that the line of sight component of the magnetic field changes smoothly from one side to the other, as it would in a spiral that is viewed slightly off-axis. Observations of Messier 87 have reported such gradients on parsec scales during some epochs, and their persistence across features argues against a chance foreground cloud. These gradients, together with the alternation of vector orientation and the presence of recollimation sites, weave a single picture, a jet that carries the memory of a helical field launched near the horizon, modulates its pitch as it trades energy with its cocoon, and survives by sharing stress between a spine and a sheath. Stability also depends on the external weather. The host galaxy's hot halo sets a pressure profile that the beam must push against. Where the external pressure falls slowly with distance, the jet can expand gently and avoid sudden overcollimation. Where the pressure falls steeply and then rises, the beam can overexpand and then reconverge, forming standing shocks. Polarization picks out these regions by showing higher fractions and cleaner orientations at the reconvergence points. In Messier 87, the locations of bright knots and changes in polarization angle suggest a sequence of such gentle squeezes, not a brutal gauntlet which helps to explain the beam's long straight run. On larger scales, interaction with small clouds or with ripples in the halo can bend a beam, yet the jet in Messier 87 deviates little. That obstinacy implies that the momentum flux is high and that a stiff magnetic spine resists lateral pressure. When small bends do appear, polarization often shows vectors rotating in a way that remains consistent with a helical wrap, rather than random scrambling, which means the field reorients rather than breaks. The role of composition shades these stability arguments. A jet rich in electron-positron pairs has less inertia for a given magnetic energy and can be easier to steer magnetically, but it can also be more susceptible to certain instabilities unless the field is strong. A jet loaded with ions has more inertia and can plough straighter, but shocks can heat it inefficiently, and the added mass can slow acceleration unless magnetic energy is ample. The measured polarization fractions and rotation behavior argue for a spine that is not pair-dominated near the base, and for a sheath that holds many low-energy electrons farther out. That mix naturally yields a beam where magnetic control is strong at launch. Inertia supports straightness downstream, and Faraday screens draw gradients that betray the helix. Stability leaves clues in apparent motion. Bright knots in the inner jet of Messier 87 show superluminal patterns, a projection effect of features moving nearly toward us at relativistic speed. Some knots have trajectories that appear straight, others drift slightly sideways before settling back. Polarization during such passages can change in step with angles rotating, as a feature rides different strands of the helix or passes through shear layers. Where a knot crosses a recollimation shock, the fraction can spike and then fall, and the vector field can snap into alignment before relaxing. The recurring pattern suggests that the jet's geometry, not just random turbulence, dictates the life of features. Stability is therefore not the absence of change, but the persistence of rules under change. The long straight line in Messier 87 is a record of rules a magnetic helix with a poloidal backbone and a toroidal sheath, a pressure profile that guides but does not crush a spine that carries momentum and memory, and a sheath that buffers the world. Polarization is the instrument that reads these rules in situ, where it shows long vectors aligned with the axis the backbone holds. Where it shows wrapped vectors and moderate fractions the sheath protects. Where it shows sudden order at bright knots, reconvergence has reset the field. Each piece fits the larger order and keeps the beam from falling into chaos. The remaining mysteries are refinements that future campaigns can test. If the pitch of the helix indeed changes smoothly, higher resolution maps should reveal vector orientation that rotates gradually across the beam rather than jumping. If the sheath buffers shear rotation, measure gradients should grow where limb brightening is strongest. If recollimation shocks are the anchors of stability, their spacing should reflect the pressure profile of the halo, and their polarization signatures should repeat with family resemblance. Messier 87 offers all the pieces of these tests. The beam's quiet straightness is a loud argument for magnetic order, and the polarized light along its length is the witness that the argument rests on writing stability not as an assumption, but as a pattern of angles and fractions that continue to hold across a galaxy's breadth. Tensions with models begin as hairline cracks that widen under the weight of better data, and Messier 87 now presses against the scaffolds that theorists built before the polarized ring appeared. General relativistic simulations of magnetized accretion predicted crescents and hinted at polarization patterns. Yet the measured polarization fraction around the ring is neither vanishingly small, as some turbulent weak field flows suggested, nor near the theoretical maximum that strongly ordered fields in overly clean plasmas predicted. Instead, it lands in a middle range that requires order on scales larger than the resolving beam, but also demands pockets of disorder or mixed rotation along the line of sight. Many simulations that reproduce the total intensity crescent nonetheless underproduce this measured fraction unless their fields remain too laminar, while runs that raise the fraction by dialing up order often thicken the ring or suppress realistic day-scale variability. The rotation behavior strains models further. Close to the ring, the inferred Faraday rotation at short millimeter wavelengths is modest, which disallows inner flows packed with cool electrons, yet just beyond the ring, longer wavelength observations reveal strong and variable rotation consistent with a denser sheath. Simulations that place most of the rotating plasma deep near the horizon tangle the vectors on the ring more than observed. Simulations that evacuate the region too aggressively reveal clean vectors, but starve the sheath, missing the large sign changing rotation measures on parsec scales. The compromise that data demand is a stratified structure with a hot pair, poor relatively transparent core, and a cooler, denser magnetized envelope, but not all numerical schemes, microphysical prescriptions or injection models naturally produce that profile without fine-tuning. Asymmetry in brightness across the ring, the leaning of the crescent also pushes models. Doppler beaming in rotating plasma explains why one side brightens, but the observed degree of asymmetry and its stability over years narrow the allowed ranges of electron temperature, magnetic pitch, and viewing angle. Some simulated flows that match the ring size and brightness swing the peak too far around the ring or allow it to drift more than the data show, while other flows that pin the peak in place slip on polarization, predicting vectors that curve too smoothly with too little tilt toward the jet axis just outside the ring. The tilts themselves are subtle in the data and sensitive to calibration, yet even when allowance is made, a persistent gentle turn toward axial alignment appears more often than the most toroidally dominated simulations allow. When the balance is adjusted to strengthen a poloidal component near the base, the models can recover the tilt, but must still keep the ring thin and the variability modest, a juggle that exposes the dependence on numerical resistivity and on the recipe for how magnetic energy turns into heat or into non-thermal particles. The question of magnetically arrested flow embodies a deeper tension. Models where magnetic flux piles up until it chokes the intake can deliver strong coherent fields and large jet power matching the straight persistent beam. They often predict polarization fractions near the ring that are slightly higher and more stable than observed, and variability that is too subdued unless reconnection bursts are forced by hand or resolved with very fine grids. Models without such arrest produce livelier patterns, but too little coherence and too little jet power. The data from Messier 87 seem to want a middle ground, a state that hovers near a rest but slips in and out, perhaps as gas supply fluctuates or as loops of field are swallowed or expelled. Many simulations can graze this regime transiently, but capturing it as a long-lived operating point remains hard because numerical diffusion and limited dynamic range in time and radius tend to shove the system toward one side of the divide. Composition is another open seam. Electron-positron pairs alter inertia and propagation effects in ways that affect both polarization and rotation. Pair-rich inner flows mute Faraday rotation, but can complicate acceleration and cooling signatures along the jet. Pair-poor flows fit the modest rotation at short wavelengths more naturally, but must still reconcile high-energy flares with limited seed populations. Simulations often assume a simple fixed ratio or treat pairs implicitly, leaving little room to test the gradients that polarization hints at. Circular polarization, small but telling, pushes on this seam further by pointing to conversion near gradients, a feature that requires sufficient low-energy electrons without drowning the short wavelength vectors in rotation. Time adds new mismatches. Day-to-day shifts in brightness around the ring seen in reconstructions, separated by nights, likely trace orbiting inhomogeneities or waves in the inner flow. Some simulations show substructure that moves and fades on similar scales, but the synthetic polarization maps either fluctuate too wildly, with vectors that jitter more than the data allow, or too smoothly as if the inner field were lacquered. The right combination of turbulence and order of reconnection and shear remains elusive at the current numerical resolutions, and with present closure schemes for how dissipation feeds electrons rather than ions. Farther out, the jet's limb brightening and transverse rotation measure gradients call for a helical field in a magnetized sheath. Yet several models that launch a powerful jet produce either a sheath that is too thin to write such gradients, or a sheath whose rotation signature does not persist. When gradients do appear in synthetic maps, their sign flips too rapidly along the jet to match the observed stretches of consistent sign, an indication that the simulated large-scale field reverses more eagerly than the real one. Even basic choices about viewing geometry and distance pile onto these tensions. The measured ring size pins the mass and distance product with high precision, but variations in electron heating prescriptions can move the effective photosphere and alter the inferred diameter by small amounts that matter at the Event Horizon Telescope scale, widening error bars in ways that finally show up in polarization fractions when correlated across days. Put together, the cracks do not break the models. They expose what must be strengthened. Microphysics of dissipation needs to feed electrons in a way that is neither too uniform nor too violent, allowing coherent polarization without erasing variability. Magnetic flux delivery must be episodic enough to graze a rest without parking there permanently. The sheath must be born thick enough to twist long wavelength vectors and carry helical memory without overwhelming short wavelength coherence. Pair content must rise outward without silencing conversion. Numerical grids must span enough radius and time to let slow-breathing cycles emerge, and enough depth to let reconnection islands grow and merge naturally. Observationally, the cure for tension is more leverage. Higher frequencies will peel closer to the photon orbit and test whether the tangential vectors tighten as expected. Denser sampling in time will decide whether the day-scale swings form patterns that simulations have missed. Joint fits of total intensity polarization, angle, polarization, fraction, and rotation across bands will corner the models into fewer compatible states. In this way, the friction between maps and movies of the sky and the laboratories in silicon does not weaken the story. It strengthens it. Tension is the sign of contact. Messier 87 presses theory until it creaks, and the creak is the sound of a picture improving one constraint at a time. New eyes gather on the horizon where gravity and magnetism divide authority, and the next tests promise to turn the polarized ring from a first draft into a closely edited text. Expanded arrays will close gaps in the planet-sized mirror, higher frequencies will press closer to the photon orbit, and coordinated instruments across the spectrum will time the breath of the engine from the ring to the distant knots. Each improvement is a wager on clarity. More stations add long baselines in directions that the first maps could not sample, shrinking the holes in the Fourier plane and reducing the degree to which assumptions must fill the space between measurements. With those gaps narrowed the thickness of the ring, the smoothness of the bright arc, and the small departures from circularity will be measured rather than inferred, and the polarization vectors that ride on top will be traced with finer steps. Longer baselines also sharpen the beam in the direction perpendicular to the known jet axis, which is exactly where the transition from tangential vectors on the ring to axial vectors just outside the ring should become most obvious if a poloidal backbone threads the base. Higher frequencies bring a second advance. A shorter wavelength sees closer to the photon orbit because the flow is less opaque and it suffers less Faraday rotation, so the measured polarization angle lies nearer to its intrinsic value. If the current reading of the ring is right, the inner vectors at higher frequency should grow more purely tangential, while the vectors in the nascent funnel should tip more decisively toward the axis. If instead unseen gradients in rotation still blur the map, the angles will diverge from this simple expectation, and the difference will reveal how much twisting plasma hides in the last light seconds before escape. At even higher frequencies, the image may resolve substructure within the bright arc, the telltale scallops of orbiting inhomogeneities, or of waves that ride the inner flow. Watching those scallops turn from night to night would let observers measure orbital speeds in units that gravity dictates, tying the pattern directly to mass and to the geometry of space-time without leaning entirely on ring diameter. Space baselines extend the reach further. A dish above the atmosphere sees through steady air and can partner with ground stations to make baselines longer than Earth lifting resolution to scales where the ring thickens into threads. With such reach, the very first bends of vectors away from tangential toward axial could be seen in a single beam, transforming a suggestive handoff into a measured gradient. Space partners also loosen weather's grip on scheduling, offering more complete tracks through the Fourier plane, and less chance that a key triangle of stations loses coherence to an unlucky cloud. Time coverage improves in parallel. Rapid switching between targets and calibrators, faster recording and purpose-built campaigns will let observers map the ring on consecutive nights without long gaps, perhaps even in continuous stretches when conditions allow. The day-scale flicker seen so far will then be sampled finely enough to show whether it follows a drift that hints at a slow precession, whether it repeats as the same sector brightens every few orbits, or whether it wanders in a way that only turbulence can explain. Polarization fractions and angles tracked at this cadence will decide whether reconnection bursts near the horizon tend to cluster, whether shocks sweep along the rim as compressive waves, or whether both happen in a mixed economy. In the frequency domain, broader and cleaner coverage over contiguous bands will turn angle versus wavelength into a solved function rather than a fit to a handful of points. Rotation measure synthesis, which in spirit peels apart layers by how strongly they twist, will let observers separate near-source rotation from sheath rotation and from more distant screens. If a thin, hot inner layer twists little, While a cooler sheath twists strongly, the synthesized rotation profile will show two peaks, separated by a gap. If instead the twist builds smoothly, a broad shoulder will appear. Either outcome will narrow the space of viable accretion states and sheath compositions. Circular polarization, faint but telling, will be hunted with greater care as calibration improves. If conversion from linear to circular modes plays the expected role in gradients near the launch, the circular fraction should grow gently with wavelength and concentrate where density and field strength change most rapidly. Detecting such a pattern would limit the number of low-energy electrons near the horizon and test whether pairs are truly scarce at the base. Coordinated campaigns across bands will carry the gains outward. If higher frequency maps show a week of increased polarization fraction on the ring without a large rise in total intensity, and if X-ray observatories record a compact flare with little radio echo reconnection, will gain ground as the preferred engine for that episode. If by contrast the inner parsec shows a month where rotation measures rise, vectors align along the axis, and optical and radio flux increase together, shocks in the sheath will stand forward. These patterns will be matched against the spacing and strength of recollimation features down the jet testing, whether an ordered packet at the base leaves a predictable chain of brightenings at the expected delays. A more complete test bed will also include proper motions measured with patience. Orbit fits to moving substructure in the ring, if discerned, will fix dynamical times near the last stable orbits. Superluminal patterns in the inner jet paired with polarization changes will fix flow speeds and pitch angles of the helix. Rotation measure gradients transverse to the beam, revisited with denser frequency sampling, will establish whether the sign and strength of the gradient persist across many knots, or change only near limbs where shear is strong. Each of these measures converts a visual impression into a numbered constraint. Theory will meet these constraints with models that expand in two directions. In the smaller direction, simulations will push to higher resolution, so that reconnection islands grow and merge naturally, shedding their energy into electrons in a way that produces realistic polarization variability. In the larger direction, simulations will reach farther from the horizon, so that the birth of a sheath with the right density and magnetic structure can be followed into the parsec region, where long wavelength rotation measures and limb brightening arise. Electron heating prescriptions will move beyond simple rules, allowing fractions of dissipated energy to flow into non-thermal tails that rise and fall in response to shocks and reconnection, rather than sitting as fixed ratios. Composition will be treated as a field rather than as a number, so that pairs can grow outward without erasing short wavelength coherence near the core. Together, these advances will turn the current corridor of plausible states into a narrower passage. The most decisive near-term tests are simple to state. At higher frequencies, do the ring vectors become more purely tangential, and do the just outside vectors tilt more cleanly toward the axis? Over consecutive nights, do sectors of increased fraction orbit with speeds consistent with the mass read from the ring diameter? Across a wide band, does the rotation profile split into a hot inner component and a cooler sheath component? Downstream, do transverse rotation gradients persist with a consistent sign across features? If the answers run as expected, the picture of a hot magnetized flow that nears a rest threads a poloidal backbone into the funnel and launches a helical jet will harden. If one or more answers surprise, the surprises will carry direction. Every deviation from expectation will point to a missing piece, whether a hidden layer of cool electrons near the ring, a stronger than expected warp that tilts the crescent with time, or a composition shift that reshapes propagation effects. New eyes and new tests thus promise more than refinement, They promise genuine discovery, a chance to see whether the rules written in the first polarized image stand firm when the language gains more words and the grammar is read with greater care. What the field implies is a reordering of roles near the brink where gravity supplies the stage but magnetism directs the play. The polarized ring in Messier 87 shows that magnetic structure is not a passive passenger in the accretion flow, but the active framework that shapes how matter falls, how energy is stored, and how a jet is born and kept straight. The vectors that curve around the darkness trace a toroidal strand wrought by rotation, while the gentle turn toward the axis just outside the ring hints at a poloidal backbone that threads the funnel. Together they point to a helical field whose pitch changes with radius, a geometry that the large-scale jet still remembers thousands of light-years away. This geometry answers old questions and raises new ones. It answers how a beam stays narrow through a galaxy's weather. The helix gives a spine and a sheath, a straight guide and a confining wrap. It answers how the engine taps a reservoir larger than the falling gas, can provide magnetic flux on the horizon, can open a channel to the rotation of the compact object, letting spacetimes twist do work along field lines. It answers how electrons are kept energetic over vast distances. Shocks and reconnection arise naturally, where helical strands compress or collide, seeding fresh non-thermal tails. Yet each answer opens a seam. If magnetically arrested phases truly occur, then the central engine operates not as a steady pump, but as a heart that sometimes holds its breath. The polarized ring implies that such pauses when magnetic pressure pushes back on the intake can briefly tidy the field and raise the fraction of polarized light without demanding a dramatic surge in total intensity. How often the heart holds, and how deeply it inhales afterward, remain open. If reconnection near the horizon is as common as the clean short wavelength vectors suggest, then thin current sheets must be a natural product of the flow, and electrons must receive a fair share of the released energy. But the precise rule that assigns energy between ions and electrons is not yet written in the light. If shocks in the inner parsec are the interpreters that translate a tidy packet from the base into downstream flares, then the spacing and strength of recollimation features must encode both the external pressure profile and the inner cadence. The field implies too a layered plasma. The small rotation near the ring paired with strong variable rotation on parsec scales argues for a hot pair, poor core, wrapped by a cooler, denser sheath. That layering sets where depolarization grows, where conversion from linear to circular modes becomes noticeable, and where gradients in rotation measure mark the helix from edge to edge. It also feeds back on dynamics because a denser sheath buttresses the spine against shear and turns instabilities from fatal bends into controlled waves. The field imposes economies on the spectrum. When order grows, the polarization fraction climbs, and the optical or X-ray spectrum often hardens evidence that acceleration and alignment share a cause. When turbulence grows, the fraction falls, and the spectrum softens evidence that the field has loosened its grip and that cooling outruns fresh acceleration. The dance between these regimes produces the slow flicker that multi-wavelength campaigns now log, and the lags between bands sketch the speed at which packets travel from the ring to the inner knots. The global implication is that time is not noise but an axis of the engine. The field speaks in motion as well as in shape, and only long patient monitoring will reveal whether the inner flow processes gently, whether preferred sectors take turns brightening, or whether the engine's breath is driven mostly by weather in the host galaxy. The deepest implication is philosophical but testable near an event horizon geometry rules. The magnetic geometry decides where angular momentum leaves, where energy emerges, and where matter is allowed to stay. Gravity supplies the potential. The field writes the script that turns potential into form. If that reading is right, then a handful of simple predictions should hold, as new eyes sharpen the view. At higher frequency, vectors on the ring should become more purely tangential, because less Faraday rotation stands between the engine and the observer, and because the sightline peers closer to the photon orbit, where rotation has done its tightest work. Just outside the ring, vectors should tilt more decisively toward the axis, as a poloidal spine asserts itself. Across wide bands, the rotation profile should split into an inner hot, lightly twisting component and an outer cooler, strongly twisting component with the sign of the twist, tracing a helical hand that does not flip at random. Over consecutive nights, sectors of high polarization fraction should drift at speeds consistent with orbits a few gravitational radii from the horizon, and when those sectors pass through, downstream knots should respond at delays consistent with the measured flow speed. Far along the jet transverse rotation, measure gradients should persist with the same sign across stretches that share a common orientation, a cartographic line that ties the far beam back to the near helix. The practical implication is that polarized light is not an accessory but an instrument. It weighs hidden electrons, measures unseen field components, times the engine's breadth, and names the sites where particles are made young again. The speculative implication is that the same grammar may hold in other systems scaled by mass and distance, from the compact engine at the center of the Milky Way to the bright cores of more distant radio galaxies. If so, then a small set of parameters will describe most of the variance, the supply of magnetic flux, the rule for heating electrons, the inclination of the inner flow and the profile of the surrounding pressure. Messier 87 has already narrowed each of these. It has shown that the field at the edge is strong, and ordered that electrons near the ring are hot enough or rare enough to leave polarization clean, that the base of the jet carries a poloidal guide, and that the sheath beyond is dense enough to twist long wavelength vectors. What remains unresolved is the choreography of change. How does magnetic flux arrive at the horizon in loops that are swallowed or expelled, in sheets that stack, or in braids that tangle and then smooth? How does the field choose between reconnection and shock, between quiet ordering and loud acceleration? How does the jet remember its first pitch across thousands of light years without letting every small push bend it? These are not rhetorical questions. They are measurements waiting for sharper eyes and longer patience. The field near the horizon has already spoken more than expected. It will speak again. The engine settles into the long night of the galaxy, and the light from Messier 87 travels for tens of millions of years before it finds an eye that can read its script. In that script, geometry guides fate. Gravity sets the potential, but magnetic structure turns it into pattern, carves a ring around darkness, and draws a line that keeps its shape across the halo. Polarized waves are the marginal notes that make sense of the main text. Angles and fractions tell where order holds, where turbulence breathes, where electrons are thrown to high speed, and where a sheath thickens to turn a quiet twist into a visible rotation. The ring is close and slow enough to watch, the jet is long and straight enough to trust, and the space between them is filled by a field that keeps its memory. The questions that remain are not failures, they are the living edge of knowledge. Does the inner flow graze a rest and relax in cycles written by supply? Do reconnection islands write the short clean bursts at the base while shocks write the long bright lines far away? Does a gentle warp lean the crescent in ways that only a long calendar can see? Each answer sits inside the light already gathered, waiting for a finer mirror, a longer watch, a steadier hand. The wonder of this view is that it turns the most extreme place in nature into a readable laboratory. No spacecraft will skim that ring, no probe will ride the jet, Yet the patterns are legible from here. The straightness of the distant beam, the quiet turn of a vector at the rim, the slow change of angle with wavelength, each is a sentence in a language that the galaxy itself speaks. The lesson is neither closure nor certainty, it is patience. Magnetic fields near horizons do not shout. They persist, and the persistence draws order from falling fire. The next image will sharpen the lines. The next season will lengthen the story. The questions will remain and the mystery will deepen, and that deepening is the point because it keeps the sky alive with possibilities.